So this is a joint work between Robert, Jinman, Arian, and Xingyu. So this talk builds on the prior work of an MLIR-based transform-driven polyhedral compiler named Polymorphous. The high-level idea of the prior work is that an expert user, for example, a performance engineer, supplies a computation kernel along with some transformation strategy to the Polymorphous tool. The tool validates the transformations in the context of the computation kernel to see if there are any dependency violations. If the transformation sequence given by the user is valid, the tool proceeds to apply the transformation and generate code accordingly. If the transformation sequence is illegal, the tool attempts to fix the violation while keeping the user's strategy as best as possible. So here is a simple example of Polybench MVT kernel written using PyDSL, a front end to Polymorphous. If you attended my talk yesterday, you would know that PyDSL generates MLIR. The transform strategy the user wishes to apply to the kernel source code is described in the MVT schedule method. In the method, the two target nested for I loops are first matched, and the user wished to apply tiling, first fusion, then tiling by 3232, followed by reordering the two inner point loops and parallelizing the outermost tile loop. The MVT schedule demonstrates the composability of the transform sequence and its separation from the kernel code. This is a primary benefit of leveraging MLIR's transform dialect infrastructure. However, one key difference is that the schedule seen here does not actually transform the payload IR. Instead, it records the transformation matrix according to each transform operation for the validation process later on. The entire code base is open sourced through the PyDSL website. So to describe the process of the validation, we give a quick review to some polyhedral concepts so that we may bring to light how Polymorphous maximally leverages MLIR's existing infrastructure. So polyhedral scheduling functions are expressed at a statement level. Here, a statement S depends on statement R. Theta S describes the execution timestamp where each instance of S is run, and similarly for theta of R. A scheduling function has the format shown over there, where the coefficients in matrix C allows us to correct the illegal transformation using skew or shifts when possible. And Farkas lemma is needed to construct the constraints linearly. The D in that complicated equation describes the dependence polyhedron. So to be able to find the correct value for shifts or skews when we need to correct the schedule, we solve the system of equations to find the coefficients in matrix C by leveraging Prisberger simplex solver available in MLIR. Okay, after the preliminary, let's dive into how we leverage MLIR. This slide demonstrates a simple kernel and using the write after read dependence between 1, the affine load of args3, to 2, the affine store of args3, to show how we can build dependence polyhedrons easily. So we leverage the affine analysis infrastructure in MLIR by writing a very small amount of code to invoke check memref access dependence on this pair of memref accesses. We need to invoke this method 3 times for the outer arg4 loop, level 0, and the inner arg5 loop, level 1, and lastly, a common loop plus 1, which is 2. So 2 dependence polyhedrons are built, one at level 0 and another at level 2. This is done precisely and accurately. Thank you, MLIR. Next, before we invoke MLIR's simplex solver, we wrote a compute Farkas right-hand side method, which converts the dependence polyhedrons you see in the previous slide into a 2D integer matrix representation, where you see on the far right-hand side, the rows represent the loop iterators and program parameters. The columns are the Farkas multipliers. Similarly, using Farkas left-hand side compute, the coefficient for matrix C, which we are looking for, are the columns of the 2D int matrix, and we seek a lexical mean solution. So the line of code to convert the transformation matrices and dependence polyhedrons into the appropriate integer matrix layout prior to invoking the simplex solver is about 850 lines of code. In summary, with very minor effort, we are able to build out a polyhedral validator, and again, thanks to MLIR. So after the initial success, we are mandated by our leadership team to see if an LLM can generate the optimization strategy for Polymorphous in place of an experienced user. Further, we want to see if LLM can generate syntactically correct MLIR code as a replacement for PyDSL. Thus, this is the second part of the talk, Agentic MLIR, LLM Plan Transform IR Generation. This is the high-level design for this part of the work. It's comprised of a router, a couple code generation agents, and Polymorphous as the validator guarding the final door for correctness. Fairly simple. Again, the goal of the system is to generate transform IR for Polymorphous. Now let's first dive into the router. So the router is really a retrieval augmented generation database. It takes an input kernel to be optimized, classifies it to be the most similar to the top K reference programs that are in its database. The optimization strategies for the reference program in the database are provided by expert humans. So the classification network is a simple dual pre-trained Kohlberg NLP softmax architecture trained using LLM-generated code and ground truth. So the router or the LLM will take in deterministic knowledge from the database on how to optimize some reference program and apply that knowledge to optimize the current input code. And this is the non-deterministic part of the LLM. So the router produces a human-readable strategy on how to optimize an input kernel shown, and it can also classify programs fairly well along the heated graph in the diagonal. It outputs syntactically correct MLIR code with collaborating code-gen agents. Here is the generated MLIR transform dialect code. So some experimental results. Oh, yes, I've flied by that page too quick. But anyway, the early experimental results show that all 30 Polybench produce code and executes correctly. That's an encouragement. Good job to LLM. And 27 had runtime better than equal to if you were just to compile the code with GCC 13 at 03. And 14 had runtime better or equal to the human written schedules that was originally published in the Polymorphous paper. So that's all. Thank you.